Graph Theory Class 5 Video 1. In this video we're going to talk about equal graphs. Let's begin with the definition. So before I say this, I want to mention that we only consider labeled graphs when we talk about equal graphs. So by labeled, this just means that the vertices have labels. Okay, so the vertices have labels. So they're called names like Alice, Bob, Charles, or maybe just A, B, C. It doesn't matter. So the definition, we say that two labeled graphs are equal if they have the same set of vertices and the same set of edges. So they have to have exactly the same vertices and exactly the same edges. And the vertices have to be called the same things. This is where the labeling is important. If one graph has vertices and they're called like Alice, Bob, Charles, and the other graph has vertices but they're called Bloomington, Ellettsville, Nashville, these two graphs can't possibly be equal because they have different names for their vertices. So equal takes into account the vertices names. And in fact, equal graphs, what it captures is just how you draw the graph. That's essentially the only sort of property that equal graphs capture. So if you have the same graph and you draw it in more than one way, then they're still considered equal. Let's just do an example to highlight this fact. So I can draw a graph like this, and I can label it. Okay? And I can draw another graph like this. And these two graphs are equal. And you use this sort of the standard equal sign, or you can just write equal. Okay, and it's clear. Like I don't really need to go into much detail why this is true, because I think it's just obvious. Like they have the same vertice set, right? The same vertices and the same edges. Okay, there's an edge on the left one from A to B, and on the right one from A to B. On the left one there's A to C, and on the right there's A to C. On the left there's A to D, and on the right there's A to D. The only difference is how I've drawn them, right? But that's a sort of superficial difference. Exactly how I draw it, it doesn't matter. That's a superficial difference. And I can make it more extreme as well. Like if I do something like that, they're still equal. There's still an edge from A to B and an edge from A to B. Okay? But what would be a non-equal graph is if I drew perhaps a different one. Okay, so it looks the same, but if I label it like this, then that is not equal to the first two graphs. And one way you can see that is, well, in the first graph, or even in the middle graph, there's an edge from A to D. But on the right graph, there is no edge from A to D. There just doesn't exist an edge from A to D. So it's not equal. Okay? Let's do another example. So that example was quite easy because the graph was quite simple. But as soon as you start having more complex graphs with more vertices and more edges, it quickly gets unclear whether two graphs are equal. Like these two graphs right here, are these graphs equal? Well, they look very different, but looks can be deceiving. You can't just go off of first impressions. So to test whether these two graphs are equal, I need to test whether they have the same vertex set. So do they have the same vertices? Well, there's Alice, Bob, Charles, David, Eve. Alice, Bob, Charles, David, Eve, Frank. Oh, Frank was in the first one as well. I just forgot to say Frank. Okay, so they have the same vertices. And now I want to test, do they have the same edges? Well, one methodical way of doing this is to draw a table. So if I draw a table like this, and what's going to be in my table is a list of all the vertices and then all the edges in the left graph and all the edges in the right graph. So I'm not going to write people's full names, I'm just going to write A for Alice. And in the left graph, Alice is connected to, Alice has an edge to Bob, Charles, and Frank. And in the right graph, Alice has an edge to Bob, Charles, and Frank. Bob, Charles, and Frank. So they're the same, and that's what I'm hoping to happen. I'm hoping that for every vertex, it's connected to the exact same set of other vertices. But I can't just do Alice, I need to do them all. So in the left graph, Bob is connected to Alice and Charles, and in the right graph, Bob is connected to Alice and Charles. Okay, so AC. C, in the left graph, Charles is connected to Alice, Bob, David, and Frank, and in the right graph, Charles is connected to Alice, Bob, David, and Frank. D, so in the left graph, David is connected to Charles, Eve, and Frank. So it's C, E, D. And in the right graph, David is connected to Charles, Eve, and Frank. C, E, D. Okay, I have to scroll down a little bit to make more room. So E and F. So in the left graph, Eve is connected to just David and Frank. So DF. And in the right graph, Eve is connected to just David and Frank. DF. And finally, Frank. So in the left graph, Frank is connected to Alice, Charles, David, and Eve. Alice, Charles, David, and Eve. And in the right graph, Frank is connected to Alice, Charles, David, and Eve. Alice, Charles, David, and Eve. And the important point is this table, the second and the third row, are exactly the same. Okay, so this means that yes, they do have exactly the same edges. Both of these graphs have the exact same edges. So, in conclusion, they are equal. Okay, and this is how you show that two graphs are equal if in general they're complicated. Sometimes it's obvious. Sometimes, like up in this example, it's obvious. But a lot of the time it's not obvious. And if it's not obvious, you need to write out this table to really prove that these two graphs are equal. Okay? That's the end of this example, and that's the end of this video.